In this video, we'll talk about the mole, Avogadro's number, and how it relates to formula, weight, and molecular mass. So, let's get started. So when we talk about chemical reactions, we're always trying to track through the total mass of materials present, because in a chemical reaction, we know that we must obey the law of conservation of mass, which says that however many grams you start with, you better end with, because you cannot create or destroy atoms. And so we run into a problem in chemistry lab in that we're used to dealing with masses by going to a scale and determining the mass of what we have, but we're not used to counting atoms. In fact, if I were to try and count out 1 gram's worth of atoms on a scale by just plain old-fashioned counting, it'd take me forever. I mean, there haven't been enough seconds in the universe for me to do that yet. So what we do to get around this is we create a frame of reference. And that frame of reference that we use is known as the mole. So normally people think about moles as these blind, cute little furry things. For chemists, when we talk about moles, we're talking about how many grams of material we need to have 6.02 times 10 to the 23rd of something. So 12 is a dozen, 144 is a gross, 6.02 times 10 to the 23rd is a mole. It's just a frame of reference. The number itself actually comes from the number of atoms present in carbon-12, and the story about how we got that number is well beyond the scope of the course, and if you want to investigate it, great, but at the end of the day, all you need to know is 6.02 times 10 to the 23rd is known as Avogadro's number and is also equal to a mole. So when we want to work in chemistry lab, we actually want to be able to count the number of atoms we have in our materials. We want to get rid of this mass component and actually make sure we're tracking through each and every atom. And given the nature of Avogadro's number being so large, you can see that it could be a little daunting to try and talk about, exactly how many atoms we have. And so we typically stick with talking about moles rather than actually applying Avogadro's number to determine the actual number of atoms. Because you can talk about half a dozen of something and know you're talking about 6. Or you could talk about 1/12 of a gross and know that you're talking about 12. So moles is just a way we use to communicate very large numbers in a very easy and convenient manner. So what we're going to do is learn how to determine how many grams we need of a molecule to have a mole, or how many grams of an ionic compound to have a mole of material. And they're both calculated relatively equally. They're very straightforward in how you do it, and we'll go through it here in a minute. But we use the terminology molecular weight to describe molecules. And molecules are materials which have a very discrete number of atoms present, no more or no less. So molecules, again, we talk about these as having concrete formulas, which, if you add or subtract an atom, you've changed the actual molecule itself. And when we work with molecules, what we want to strive to use is the most accurate molecular weight we can get. With compounds, we're also going to strive for the same thing, but rather than calling it molecular weight, we call it formula weight. And it's just a very subtle difference between the terminology and what it represents, but it is worth noting that when you talk about molecules, you use molecular weight or molar mass, and when you talk about compounds, you use formula weight. So let's talk about how to get the molecular weight. Well, the molecular weight is simply the sum of each atom's mass in a material. So in the molecule ethane, for example, the molecule itself is made out of 2 carbons and 6 hydrogens. Well, to get the molecular weight, what we have to do is add the mass of 2 carbon atoms together and add that to the mass of 6 hydrogens. And you can see there that I've gone through and done the calculation. So 2 carbon atoms at 24 grams, 6 hydrogen atoms at 6 grams. Add the two together, you get 30.070 grams. after taking into account your rules for working with significant figures. So if we're going to talk about a mole of ethane, then we're talking about 30.07 grams of ethane. So if I have 30.07 grams of ethane, I have 1 mole of ethane, or I have 6.02 times 10 to the 23rd ethane molecules present. So these three quantities are all describing the same amount of material. One's in terms of mass, and the other two are in terms of how many molecules are actually present. If we switch to talking about ionic compounds and formulas, rather than dealing with a discrete number of atoms, we're talking about ratio of cations to anions. And so whenever you have a compound, you should first check to see that you have the lowest ratio of ions to each other, because if you don't do that, then you're going to get the second part wrong. So if I have, for example, cadmium and chloride ions, I could have any number of actual atoms present. But what we base the formula weight on is the ratio of cadmiums to chlorides, because the ratio of the cation to anion is what defines the properties of that material. So if you have a cadmium with a +2 charge and chlorides with -1, then when you bring those two ions together, you need to have 2 chlorides for every cadmium. That is the lowest ratio of cation to anion you can have. Therefore, when you actually calculate the formula weight of calcium chloride, you would just take the mass of 1 cadmium atom and the mass of 2 chloride atoms to get the formula weight. So in this case, if you have 110.99 grams, you have 1 mole of calcium chloride, or 6.02 times 10 to the 23rd calcium and chloride ion units together. So we can use molecular weight and formula weights to convert mass into number of particles, or just keep it on a more general term and talk about moles. So we need to be able to go from mass to moles, moles to particle, or any combination of those three. Likewise, we usually use moles as a transitional element, poor choice of words, as a transitioning point when we're doing chemical reactions to convert one material into another one. So most of the class, both Chem 151 and 152, will be about getting our starting material into moles and then using moles to determine how much material we should get into in stoichiometry when we talk about that in the next chapter. So that'll wrap up this discussion of moles and molecular weight and formula weight, and we will see you in the next video.